Okay, so now we're going to look at how do we find the limit if we don't have the graph. And we're going to start by looking at a graph and then trying to figure out a method to do it without the graph. So we're going to consider this function. And by the end of today, you should be able to do the limit just by seeing the function, and you won't need the graph over here. But we're going to start off by looking at the graph and comparing. So there's two things we're going to do here in this table. The first thing we're going to do here is find f of a using the equation. Now, a is like our target value, I call that. Whatever the limit is trying to, whatever the limit as x is approaching. So in this one, our target value is 0. So let's just plug that target value, that x value 0, into the function up here and see what we get. Well, f of 0 comes out to be -2. All right, so we don't really know what that tells us about a limit. It's just plugging in the x value and seeing what we get. And now we're going to go ahead and use the graph over here to find the limit. So the limit as x approaches a. So again, here we're going x approaches 0. So 0, as x approaches 0, we've got to check both sides by the limit existence theorem. First, we check the limit as x approaches 0 from the left. So we're here on the curve. And we're approaching a height of -2. Now we're going to approach x approaches 0 from the right, and we're here on the curve. Whoa, just dropped my pencil. We're here on the curve, and we're approaching that same height of -2. So the limit existence theorem says that if the limit from the left is going to the same place as the limit from the right, then the limit as x approaches 0 of this function must be -2. They're both going to the same height. So what we notice here is that these two values are the same. So if we didn't have the graph and we want to find the limit here, couldn't we just use the equation, plug in the x value, and that answer should be the same as that answer? And that's how we do it. It's that simple. Of course, it gets harder than that. But that's how we start. These two things, f of c or f of a I'll use, will be equal to the limit as x approaches a. These two things will be the same if the function's continuous. At that x value. Then we can say these two things are equal. So anytime they ask us to find the limit, we're going to kind of cheat it, shortcut it, and just do direct substitution, I call that. All right, so that's the first way we're going to find a limit without a graph. But you have to know that the function is continuous at that point. So let's just review quickly from Algebra 2 a general definition of what it means to be continuous at a point. So like at this x value c, if I draw the curve to be continuous, I can't pick up my pen or anything. So of course the limit's going to be the same thing, because if there were a hole here, the function would not be continuous. So then f of c wouldn't be defined. But since it's continuous, we know that there's not a hole there. That is defined. I'll just put a dot there to really make it stand out. That's the same thing as if I just drew a curve straight through it, right? So that height right here is f of c. I should write it this way. I'll write it as a point. That point is c comma f of c, right? Because the function's continuous, I know that f of c is going to be right there, and it's going to be the same thing as where the function was headed on its way in and where it is on its way out. So that means from both sides, it has to approach this height of f of c. So of course the limit is the same thing as f of c when the function's continuous. There's no breaks or anything. If I had a function that wasn't continuous, now I can't say that the limit is equal to f of c, right? Because f of c is down here, right? This y value. In this one, the limit as x approaches c does not exist. Sometimes looking at a counterexample helps. So in this case, I can't say that f of c is equal to the limit as x approaches c. Those two things are not the same because the function's not continuous at c. But if the function is continuous, which look at this function, it is, right? I can trace it without picking up my pen anywhere. So I'm going to be able to just use f of c as my limit. So that's kind of the big idea here. So now let's look at this next one. the limit as x approaches 2 from the right. So now our target value is 2, but it's only from the right. So first of all, this column here just says find f of a. It doesn't worry about left or right. You're just plugging in f of a. So our target value is 2. We don't have to worry about right. All right, and f of 2 should turn out to be -4 when I plug it into the equation up here. So now let's find the limit of the graph. So we're saying the limit as x approaches 2 from the right of f of x. So if we look on the graph over here, as we approach 2 from the right, we're coming over here. Okay, and so we know that the limit as x approaches 2 from the right is, it looks like a y value of -4. So based on what we just learned, since the function's continuous, this means that the limit as x approaches 2 equals -4. Oops, I have to write up what function I'm finding. The limit of f of x equals -4. So if I know the limit of f of x equals -4, then by the limit existence theorem, right? Don't forget that limit existence theorem. It says that you have the limit. You can write it either way. If I say the limit as x approaches 2 of f of x equals 4, then that implies that the limit from both sides, from the right, is equal to the limit from the left. And they're both equal to that same value. Because for a limit to exist, the limits have to be the same from the right and the left. So because I know f of 2 equals -4, then I know the limit as x approaches 2 equals -4, and that means from both directions. I don't care left or right. So that's how I would find this limit without the graph. As x approaches 2 from the right, I would just plug in the 2, and I would get -4, and that would be my answer. It wouldn't matter if they asked me to find it, whoops. It wouldn't matter if they asked me to find it from the left or from the right. Okay, now we kind of have an idea of how to find the limit without the graph. That's exactly what we're going to try here. It's asking us to find the limit as x approaches 10. So first I'm going to plug 10 in this column to find f of a. So our target value is 10, so we're going to plug a 10 in here, and we should get 4. So what that means is that since the function's continuous, we know that the limit as x approaches 10 is also 4. So you can see how we just cheated it. Why did I not use the graph? Well, because we don't even have, the graph ends, what we see ends at 6. So we have to keep going up here and go all the way over to 10. But I know the graph's continuous, and I know what's going to happen. Because the graph is continuous, when they ask me to find the limit, I can just cheat instead and just plug in and do direct substitution. All right, so let's summarize what we just found out. When a function is defined and continuous at a value, x equals a, so this is the key. We have to know the function's continuous, okay? How can the limit be found analytically? That means without the graph. That's what analytically means. I like to say algebraically. All right, and so what we found out was the limit as x approaches a of f of x is equal to, just using direct substitution, f of a, provided that f of x is continuous at the target value. Now, the function can be it doesn't have to be continuous everywhere, just at that single value. And we'll see that come into play here a little bit, right? So this is very powerful, this thing right here we're using. If the function's continuous, whenever they ask me in calculus now to find a limit, I'm not going to do that. I'm going to cheat it and just find f of a and then say, well, I know because the function's continuous, that's also the limit. All right, so that's what we're doing here in these. So here's some practice problems. So they're asking me to find the limit of this function. This function is a polynomial. We know polynomials are continuous at all x values, so we're good to go. It's continuous, so instead all we need to do is plug our target value in. I'm going to refer to that as direct substitution. So we try direct substitution. We know the function's continuous. When I plug in my 3, I do all that out. You could pause the video here if you like and see if you get the same thing as me and make sure I'm right. I got 3/2 when I did it in practice, okay? So I know the limit is 3/2 because I'm saying the limit is going to be equal to direct substitution, and because the function's continuous, they're both going to be equal to the same thing, which is 3/2. All right, so direct substitution. Okay, how about this function? Is this function continuous everywhere? Well, this is called a rational function. Just some review from Algebra 2. This one, by the way, I'll just write this down. This was a polynomial. Your definitions here are a rational function. Its definition is pretty simple. It's just one polynomial divided by another polynomial. So when I have a rational function, which is what this is, it's continuous everywhere except at certain x values. Like we'll say it's continuous everywhere except x cannot be, or I don't want to say that because I said except, so I'll just say x equals, some numbers. We'll just list a couple. In this case, I don't care where it's not continuous. I just care, is it continuous at that x value? Here's how you could tell. If you plug in x, well, I should tell you this. A rational function is not continuous when the denominator equals 0. So if we're trying to divide by 0, you cannot divide by 0 in math. What's 5 divided by 0? You can't get a number. What's 7 divided by 0? Division breaks when you try to divide by 0. So anytime that you divide by 0, the function is not continuous. So if I plug 3 in here for x, do I get 0 in the denominator? I do not. I get 3. So that means the function is continuous, so I don't have to worry. The function is continuous at 3. That means direct substitution will work. So I plug in my 3. I go 5 times 3, 15. So I did this already, sorry. So I got 17/3. Again, you can let me know if I did something wrong. Reach out to me. Here's another function, another type of function. And what we're going to call it is, I'm going to call it, it's a rational type of function. Why do I say that? Well, because it's not necessarily a polynomial divided by a polynomial, but we still have this mechanism of division, and all we really care about is that we don't divide by 0. We do not want to divide by 0. If we divide by 0, this method's not going to work because the function's not continuous. All right? The reason I can't call this rational is because this is technically not a polynomial when you have a square root of x in there, okay? So I want to check at 2. If I plug 2 in, do I get 0 in the bottom? I do not. So that means that's great. The function's continuous at the target value 2. Now they want the limit from the left, but since the function's continuous, I could care less about left or right. I'm just going to find f of 2. I'm going to plug in my target value. And what do I get? I get 1/3. That's what the limit, just keep in mind, that's what the limit as x approaches 2 is. I'm just going to write f of x. I don't want to rewrite out that whole function, right? Because the function's continuous, I know that f of 2 is equal to the limit. Now the next step in the logic is the limit existence theorem. I'll just say that. The limit existence theorem says that if your limit exists, then the limit from the left and the right must be the same, and they must be equal to that number, whatever the limit is. So that means, by the limit existence theorem, the limit as x approaches 2 from the left, I'm not going to write out the whole function, I'll just say of f of x equals 1/3. So that's our answer. Do you have to show me all of these steps? No. You just have to understand them. In the notes, I'm writing them all out. I'm explaining what's happening. But like when you do the practice, you just have to kind of figure out what the answer is. All right. So here's another function here, a sine function. We know that the sine function just kind of does this. So it's continuous, right? Whether we shrink it, shift it, it's continuous everywhere. So sine functions are nice. We don't have to worry about checking if they're continuous at our target value. They're always continuous. So that means direct substitution will work. We can cheat finding the limit by just plugging in pi over 2. So then sine of 2 times pi over 2, right? I do that out and I end up getting 0. So our limit is 0. Because the function is continuous, we can just say since f of pi over 2 is 0, then the limit equals 0. So maybe I should write this all out. The limit as theta approaches pi over 2 of sine of 2 theta equals 0. That's technically how you're supposed to kind of write it out. All right, E, we have a rational type of function. I can't call it rational because cosine is not a polynomial. Remember, the strict definition of a rational function is a ratio of polynomials. okay? But we call it a rational type, and why is that important? We just want to make sure that we don't get divided by 0 at our target value. So when I plug in 2 pi over 3 for theta, I do not get 0, so we're good to go. I'm going to do f of 2 pi over theta, plug that into the function, so I get cosine of 2 pi over 3. I said 2 pi over theta, sorry. 2 pi over 3 over 2 pi over 3. So when I do that out, I end up getting negative 3 over 4 pi after I simplify. You can let me know if you get something different. Or, maybe I made a mistake. How about the logarithmic function? Well, the logarithmic function looks like this. Okay, yeah, it's shifted left and right, and this one happens to have some kind of shift left or right, and it's also reflected. But generally, the function's continuous everywhere that there is a function. There's whole sections of x's where there's not a function, but our target value won't really be there. How would you know? When you plug it in, we cannot take the log of a negative number. So if I plug in 9 and I end up getting a negative inside my log, that's no good. The function's not continuous, and this method won't work. We got to try something else or figure something else out. In this case, there wouldn't be a function, so it's not going to happen for logs. So when we know that the function's continuous pretty much everywhere that it's defined. So if I plug in 9, I definitely don't get a negative number in there, so we're good to go. So I can do f of 9 because the function will be continuous. So I go log base 8 of 11 minus 9 is log base 8 of 2. And remember what a log means if there's all numbers plugged in. It's an exponent. It's sort of a question. It's saying what is the exponent of the base 8 that equals 2. So if I wrote that out, it's saying what's the or I'll use a question mark. What would be the exponent of 8 that would equal 2? That's what this means. And we know that that's going to be equal to what? I can cube root 8, so 1/3 power. So I would say the limit as x approaches 9 of log base 8 of 11 minus x is equal to 1/3. That's a 3. Okay, so remember, if the function's continuous, the limits are very easy. We try direct substitution. We're always going to try this method first. By the time the school year ends, we're going to have so many methods for finding limits. You're going to hear me stressing, always try direct substitution first. Try direct. You're going to forget about it because it's so easy. But we're going to have to always remember to always try that first. Okay? So that brings me to the point that a lot of the limits that you'll see on the AP test or even like by the end of this unit, direct substitution will fail, okay? So, but you still have to try it first. So, in other words, I plug in f of 3 and I don't get a number. Here I got 3/2, so it worked. It did not fail. But sometimes I'll plug in f of 3 and I won't get a number. I'll get there's a discontinuity at the function. What would I get? What would that look like? Well, most of the time we're dealing with rational functions when that happens, or rational type functions. And we already said before that if I try to do f of negative 3, I'm going to get divided by 0. If I plug negative 3 in here, and you could pause the video if you like and do it, you'll get 0. If I plug 1 in to this function, I'm also going to get 0 in the denominator. And when I try here, again, by the way, this was the limit from the left, so I just tried direct substitution. This is the limit from the right. I tried direct substitution again, so I would just try to plug in 1, and I get divided by 0. So this is what it looks like when direct substitution fails. Dividing by 0, trying to, I should say, gives you an undefined number, meaning we don't know what it is. Whoops. So what do you think is there on the graph? Well, there's a discontinuity on the graph. If you remember back to Algebra 2, there are 2 different types of discontinuities. So notice this function was the same every time. We were just plugging in different values. We plugged in a negative 3 and we plugged in a 1, and both of those failed, which means the graph must have a discontinuity there. Well, here's a look at that graph. And you can see at negative 3, we do have a hole. So that's a discontinuity. That's an x value that doesn't have a y value. Now looking at the graph, if I gave you the graph, it'd be very easy to find the limit. You could just see that they're going to that same height, whatever it is. It looks like it's around 1/2, and it actually is because I give you the coordinates of the hole up here, right? So it's easy to do on the graph, but again, if you were given this without the graph, you were just given this equation, and they asked you to find the limit as x approaches -3, you would plug it in, try plugging it in, thinking, okay, the function must be continuous, and direct substitution would fail. And now it's like, uh-oh, what do we do now? Okay, so that's going to be the next step in the process. What happens when it fails? What does that mean? Do we just stop and say there's no limit, or can we keep going and find the limit? And we can see here from the graph that we should keep going sometimes because there is a limit, even though I'm going to say f of -3 is undefined, so it doesn't help us in our quest. There's a discontinuity here. Whoops. It depends. I hear all different teachers' textbooks call them different discontinuities, but there's types. I call this one removable, which is a hole. We're going to learn why it's called the removable discontinuity. Some teachers call it a point discontinuity. I would say that you probably hear that more often than you hear my thing. All right? That's probably what you learned in Algebra 2, I would guess. So we're gonna, I'll use that language for now. The other spot where there was a discontinuity is when I plugged in 1, I got divided by 0, and it broke our whole idea of the function being continuous and direct substitution working. So direct substitution failed at 1, and we can see that we have a different discontinuity. Yeah, f of 1, I'll write that down here, is undefined also, but it's for a different reason. It's a different type of discontinuity. At this x value, we have a vertical asymptote. And I call that a non-removable. Again, you'll see why I use that language in a little bit. A non-removable discontinuity. I would say that your teacher, Mrs. Davidson, probably called it, or whoever you had, might have called it an infinite discontinuity. That's because the y values will, if there's a vertical asymptote, as the graph gets close to it, it just goes down to infinity or up to -infinity. Those are kind of just the two choices. It can't cross the asymptote, the vertical asymptote. It has to just shoot up or down forever. Whoops, didn't mean to do that. So there's two types of discontinuity. I like this language better because when we don't have the graph, this is going to help us. Here's how I would say you can remember it on the graph. Removable means you can fix it. It's fixable on the graph. If I were to just define f of -3, I would cheat and define it there by just filling in the hole. Now the function would be continuous. I can fix that discontinuity. In other words, I can remove the discontinuity very easily. And now the function would be continuous, and finding the limit is no problem. Okay, and that's actually what we're going to do. But when I have a vertical asymptote, that's a non-removable discontinuity. That's not a fixable discontinuity. I could never make the function continuous. Like if I just define f of 1, I could define it here. The function still is not continuous. I could define it up here. It's still not continuous, right? So you can never fix it. Whereas the hole is pretty easy. If you just define f of 3 right there in the hole, right? I could define f of 3 instead of at the hole. I could define it up here, but now the function wouldn't be continuous. But there is a way to fix it. There's two things I want to point out. The first thing is that holes can be fixed. That's why they're called removable discontinuities. Vertical asymptotes cannot be fixed. Fixable discontinuities still have a limit, because if I could simply fill in the hole and make it continuous, that means the limit was already going to the same place on both sides. It had to be. That's the only way you can make it continuous. When you have a vertical asymptote, the non-fixable ones, you can never make them continuous. You can't find the limit. So if we have an unfixable one, we're going to just stop. Whoops, I didn't mean to do that. If we have an unfixable one, we're just going to stop and say you cannot find the limit and not continue on. But if it's fixable, we have to continue on because you will be able to find the limit. And the way we find the limit is by filling the hole. Now, the other thing I want to stress here is when you fill the hole, you've just made a different function. I just changed the function. These functions are the same. So let's say the original function was f of x, and now when I fill the hole, we're going to say that's called g of x with the hole filled. Discontinuity fixed at that x value. Those are close functions. I'll call them agreeable. I'm running out of room here. Let's say it this way. Agreeable functions. That means they're almost the same everywhere. They disagree at this one spot. But what's going to happen with agreeable functions is if the limit as x approaches our target value of g of x, it's now continuous, we can just find g of a, and that's going to be my limit, right? Those two things are going to be equal. And then g of a will also be the limit of f of x, because the only difference is I just erase that, and now I have f of x, right? This is g of x. This is f of x. Do the limits change? No, it's still the same limit, whether the hole's filled or not. Filling the hole just allows me to make the function continuous, and I can go ahead and cheat it. So it's almost like a double cheat, all right? So let's summarize everything we just talked about. That was quite a bit. And this video is going to be long. I'm very sorry. I may actually make it 2 parts. So for this guy, finding the limit of undefined values, the first thing I do is when I don't have the graph, how do I figure out if it's if it's a removable or fixable, like a hole, or if it's not fixable, like an asymptote? I plug in the target value, I get 0 on the bottom. That doesn't tell me if it's a hole or not. It tells me it's either a hole or a vertical asymptote. The top will tell me which is which. If I get a 0 up top, that would be a hole, and this one is a hole. If I get a non-zero number up top, that's a vertical asymptote. This one is fixable. That means there's a limit. Let's keep on keeping on. And this one is not fixable. There's no limit. Let's just stop wasting our time. Okay? In these, we will still go try to find our one-sided limits just because. You'll see in a little bit why we do that. All right? This one would be a non-zero. So that's how you can tell. There's 2 things here. 0 in the bottom. I want to say it this way. I don't want to say 0 on the bottom. Divide by 0. Divide by 0 means that there is a discontinuity, and that also means that our direct substitution fails. The second thing is, let's look at the numerator. If the numerator is also 0, because we know there's a discontinuity, the numerator will type it for us. If the numerator is also 0, we'll say that it's fixable or removable discontinuity, which is really just a hole. And again, you guys might have used the language point discontinuity. Those are good. If the numerator is not 0, it's not fixable, so then we don't find the limit. This is the kind that we can fix and carry on and find the limit. So you're going to hear me talk as we move through this unit, like this is the rest of the year. We like when we get 0 over 0 because then we can keep finding the limit. We can keep going. We can fill the hole. All right, so they want us to go from the graph and just show us that just because there's a discontinuity doesn't mean that the limit doesn't exist. Sometimes you can still find the limit, other times you cannot. So notice our target value here is -3, and they're just saying from the graph find the limit. So there's a hole there, and we already found this limit. We said it was 1/2. Okay. Now what I want to do before I jump into these 2 limits is I want to just find the limit as x approaches 1 of this function. X squared plus 4x plus 3 over x squared plus 2x minus 3. So I want to find this limit from the graph. So if I look on the graph as x approaches 1, let me do this in different color because there's already a lot of green there. Let's do this purple. As we approach 1 from the left, we're down here on the graph. We're going to -infinity. And as we approach from the right, we're here on the graph going to +infinity. So these limits, the limit does not exist for 2 reasons. One, because infinity and negative infinity are not real numbers, L, right? It had to be a real number. And then two, they also don't agree. One goes to positive infinity, one goes to negative infinity. So that limit doesn't exist. Now they're asking for the one-sided limits. Technically, those limits do not exist. So we are still going to go ahead and find the one-sided limit, and we're going to, again, without the graph, we'll come up with a method to be able to do this. So the limit as 1 approaches 1 from the left, we had negative infinity. It was going down, right? This purple thing. So we said that was going down. And then 1 from the right, it was going up to infinity, a height of positive infinity. So we can still find the one-sided limits even if there's a vertical asymptote. Okay? So now we're going to talk about how do we do this without the graph. Okay? And that's really the key here. So we're always going to try direct substitution first, and it will fail. So what does that mean? I'll say if, I'm going to zoom in a little bit. I need some real estate here. If direct substitution fails, that means we would have gotten divided by 0. I'll put it in parentheses, right? Then we have a discontinuity at the target value. Now we got to figure out what type of discontinuity. So that's step 1. Step 2, let's type it. And how do we do that? We do that by also plugging our target into the numerator. And so if we get 0, let me write that neater. If we get 0 in the numerator, that's a removable or fixable. I'll say removable or fixable, or a hole on the graph, or we've called it point, all of those words, discontinuity. What that means, though, is that we can fill the hole but now we have to do it algebraically. So we can fix, I'll say, the function so that the target value no longer gives you all right, so if we get 0 over 0, that means we can fix this thing. We're going to do some algebra. Remember, we don't have the graph now. So we're going to fill the hole with some fancy algebra, some fancy footwork. I don't know if you've ever seen myself or Mr. Tong on the basketball court, but that is the definition of fancy footwork. I can tell you that. All right. Type B would be if we get a non-zero number, something other than 0 in the numerator. That means we have a non-fixable or non-removable discontinuity. Non-fixable. I'm not going to write all the other, well, I guess I will. That's a vertical asymptote. I'll just abbreviate on the graph. You might have heard of that as infinite discontinuity. It's that type of discontinuity. Yeah, so any one of those types. And what that means is that there is no limit. So the limit does not exist. Always, always, always. Limit does not exist. So if I get non-zero over 0, I'm just sort of done. The limit does not exist, okay? Unless they're asking for a one-sided limit, then we go a little farther, even in this case, and we'll discuss that a little later. But for right now, we're just talking about limits, not like from left to right, okay? So the key here is that when you get 0 over 0, you're going to fix the discontinuity and then retry direct substitution. It should work because what you've done is you've made that agreeable function. You've filled the hole. Now it's continuous. Direct substitution will work. So what I say is, though, I say, you know, some fancy footwork, some fancy algebra. There's going to be different methods in which ways that you can fix the discontinuity. There's 3 main ways to do that, types that you see. So I've made you different types that you'll see commonly, and we'll learn how to do each type. Okay, but for right now, I'm not going to worry about how do you do each type. I just want to worry about the big idea. A little later in the video, or like I said, this is getting long, I might make a separate video that just works through some examples of like, when we have this type, this is how we fix the hole. When we have this type, this is how we fix the hole. All right, so this one here, the function we've been dealing with at -3, we know there's a hole, but let's prove that. Let's try. We always, always, always try direct substitution first. So we plug in -3 and we get divided by 0. Darn it. What does that mean? That means currently we can't find the limit. Okay, now to decide if we can go further or not, we also have to plug -3 into the numerator. So when we do that, we also get 0. So now I'm like, yes, that's good. This is a removable. So let's fix it. Now we don't have the graph. On the graph, it's really easy to find. Right? We can just kind of look and say, oh, the limit is 1/2. Okay, and this equation is that graph, so the answer will be 1/2. But how do we fix it with some algebra when we don't have the graph? Well, the first method is if you have a true rational function, meaning a polynomial divided by a polynomial, a lot of times you should be able to factor it, because if you think back to some skills from Algebra 2, if f of -3 equals 0, now I'm not talking about the whole rational function, I'm just talking about this polynomial on the bottom. If when I plug that in I get 0, that means that x plus 3 has to be a factor of it. Okay, if you guys recall like the remainder theorem and all that kind of stuff. And since I also get 0 in the numerator when I plug in -3, that also means x plus 3 must be a factor of it. So that is how we fix the problem. We make a new agreeable function. We factor the top and the bottom, and we know because we got these results, we know x plus 3 has to be a factor in both. So what I can do is I can now reduce those right out of there. I want to stress I'm making a new function. It's different than the original. They're agreeable functions. And now it's going to be this thing. I don't need the parentheses anymore. Whatever was in here, it's going to be that rational function. This function and this function are not the same. They're agreeable. They're the same, not 2 G's, 2 E's. They're the same at every single x value except our target value. Our target value makes this function undefined, but it's going to make this function defined. It's actually going to have a value, a y value, and that's going to be our limit. So how do we find those things? Well, we just go ahead and factor. So I was just cheating a little bit and showing you how you can kind of get a head start on the factoring based on your results up here. So if this is x plus 3, then this has to be x minus 1, right? And then on the top, if that were x plus 3, then that would have to be x plus 1. So after I reduce and I make my new agreeable function, I get this. So now if I find the limit of this function, that's also going to be the limit of that function, because all I did was fill the hole. Now it's continuous. Now I can cheat the limit by just doing f of -3. So when I plug -3 in, I no longer get divided by 0. Look at that. I get divided by -4. Now up top, I get -2. So 1/2, because this function's continuous, 1/2 is the limit of that function. And because they're agreeable, that limit is also that limit, because it's just a hole. So you kind of tie it all the way back through logic that we built, and we don't need to express that every time. You can just go through the steps and find the answer. That is the limit of the original function. So this is one of the types of ways that we will, methods that we will use the fancy algebra, I'm going to say if it's a polynomial over a polynomial, we're just going to factor the top, factor the bottom, and do our cancellation of the common factor there. So notice this no longer has a discontinuity at -3. We filled the hole, but it still has a discontinuity at x equals 1. It did originally, and it still does. That's because I cannot cross this out with that, right? So it's non-removable, which means, yeah, we knew that. Remember on the graph, at x equals 1, there was a non-removable discontinuity. I can't fix it. There's just nothing I can do about it, all right? So here's a little summary for us. You can pause the video here, read this, and try to fill in the blanks. Okay, welcome back. So I would say that an infinite discontinuity is a vertical asymptote. Since the y values approach one specific value from both, they do not approach one specific value from both sides at a vertical asymptote. Then the limit does not exist. So remember when we get the non-zero over 0, something like 5 over 0, the limit doesn't exist. But if we're trying to find one-sided limits, we're going to continue on. So now the question becomes, how do I figure that out without the graph? Yeah, looking at the graph, I know as I come into this function from the left of 1, it's going down to -infinity. How do I figure that out down here without the graph? I'm going to use something I call zero positive. It's a little different than what most people will use, but if I write a number like this, an expression, that means a really small number, positive number, sorry, really small positive number. And it gets ever smaller and smaller and smaller. So when I plug in 1 to this thing in the bottom, I get 0. But if I plug in a number really close to 1 on the left, like say 0.9 or 0.999, I'll get a number really close to 0. But I got to decide if it's positive or if it's negative. So you could just use the simplified function, by the way. So even though it doesn't help us when we simplify it, we're still going to use it. So this way I can find out if it's positive or if it's negative. So when I plug in a number coming up on 1 from the left, like say 0.9, I get a negative number on the bottom. So I'm going to say that that's like a 0 negative. And the real thing you're supposed to do here is get even closer from the left. So like 0.99, I would get still a negative number. And then 0.99999, I'd still get a negative number. They would just keep getting increasingly smaller and smaller and smaller, okay? So what this means is ever smaller numbers, negative numbers, which means this number overall is going to go to infinity or negative infinity. It's going to. Because think about when you divide a number by a small number like 1/10, but then you make it even smaller, 1/100th, and then you make it even smaller if you divide by 1 over 1,000. Well, how do we simplify dividing by a fraction? Instead, we multiply by its reciprocal. So instead of dividing by 1 over 100, I multiply by 100. Instead of dividing by 1 over 1,000, I multiply by 1,000. So whenever your denominator gets ever smaller and smaller and smaller and approaches 0, your overall number is going to go to infinity. So we just have to decide, is it positive infinity or negative infinity? Well, I know that bottom number is going to be negative. Now I can just plug the 1 in. I don't have to do like 0.9 or whatever because it didn't make the top 0. I only have to do that on the bottom where it makes it 0. If I plug 1 in up top, because our target value is 1, I get 2. So 2 is a positive number. A positive divided by a negative gives me a negative. So again, think about it like this. I have like 2 over, say, negative 1/10. That's if I plug in like 0.9. If I plug in 0.99, I have 2 over negative 1/100th, and so on and so forth. So if I multiply this by negative 10, I get, that's a multiplication dot, I get negative 20. If I multiply this by negative 100, I get negative 200. So all of a sudden that number gets larger and larger and larger. It'll just keep going to negative infinity. So that's how we figure that out. So when you have a non-zero over 0 and you're doing a one-sided limit, you know the top won't be 0, so I don't have to worry about that. I just have to worry, is it positive or negative? You know the bottom will be 0. So you're just going to plug in a number really close to that x value, our target value, and find out if you get 0 negative or 0 positive, because you know the answer is going to be, there's only two choices, infinity or negative infinity. Remember what I said on the graph. If you have a vertical asymptote, the only thing the graph can do is shoot up forever or shoot down forever. So it's either going to be positive infinity or negative infinity. So let's look at this one. If we simplify this function, the limit as x approaches 1 from the right of x plus 1 after we did the factoring and simplification. Now I'm plugging in a number really close to 1 from the right, like I'll say it this way, f of 1.1. If I plug in 1.1, I get a really small number like 0.1 or 1/10, but it's positive. So I'll say I get a really small number or an ever smaller number that's positive. I call that 0 positive. Up top, I can just plug in the target value 1 and I get a positive 2 again, right? So now a positive divided by a positive is a positive infinity. So this method here, it's the same thing. Take the simplified function, plug in 0.9. I like to really explain it a little more than just doing that so you understand what's going on. So the limit from the right is infinity. The limit from the left was negative infinity. If we look at the graph, that's what we got, right? From the right, we were going up to infinity. From the left, we were going down to negative infinity. So this is another method. You know, we talked about the fancy algebra. One method was the cancellation process through factoring. This is another method, which is called rationalization. And I think what we're going to do is, no, I'll keep going with this one, and we'll pick up with worked examples in the next video. I'm going to finish with this one here. So the graph of this function is pictured to the right. So they want us to find the limit as x approaches 3. Okay, so I can see on the graph there's a hole there, but if we didn't have the graph, we would have to just try direct substitution with our target value. So our target value is 3. We plug in 3, we get 0 on the bottom. I say, uh-oh, it's undefined. There must be a discontinuity there. I'm also going to plug the 3 on top to see if it's removable or if it's non-removable, because they just want the limit as x approaches 3. So my answer, if it's non-removable, my answer is does not exist, and I'm done. So when I plug 3 in the top, I get square root of 4 minus 2. That's also 0. So now I know that it's a hole. It's removable. So I want to go ahead and remove it. The problem here is this is not a polynomial as we discussed earlier. So I can't just factor it and cancel. Now what I do know is that because when I plugged in 3, x minus 3 must be a factor on the bottom, because when I plugged in 3 I got 0, and the same thing happens up top. There must be a factor of x minus 3 up top. And there actually is. We can tease them out. Like the bottom, it's already there. I see it. We're going to be able to tease an x minus 3 times a bunch of other stuff out of the top, or maybe it's just an x minus 3 on its own. I don't know. But this guarantees me, the idea that I plugged in 3 and got 0 guarantees me that I can get an x minus 3 out of the top, and then I can do my cancellation process and we're good. All right, so the problem is you can't just factor when there's a square root. So we're going to do something called rationalizing. Your whole math career, you've been rationalizing denominators. In this class, we're going to actually rationalize the numerator here to find a limit. So what it means to rationalize something is this is irrational because it's got a square root, like the square root of 3 is irrational. So I want to rewrite this without the square root anymore. I want to make it rational. So if you had an irrational number in Algebra 2 like square root of 3 plus 2, how would you rationalize it? You would multiply by what's called the conjugate pair. It's exactly the same number, but the signs are the opposite. So when you multiply these out, you'll get a new number that doesn't have a square root in it. And actually, you know what? It's a good exercise to do that because it'll tie into what we're doing here. So if I want to rationalize this number, I multiply it by its conjugate. I'll get a new number that's not irrational. So root 3 times root 3 is 3, so it'll be a rational number. Now, I do the first times the first. I'm not going to do the first times the last and then the last times the first. I'm not going to do those because they're the same thing. This is going to be a negative version of that times that because a negative times a positive. This will be a positive version of the same thing. That's what happens with conjugate pairs, right? X plus 3 times x minus 3. If you multiply those out, you just get x squared minus 9. You don't get that middle term because they cancel out. That's why we choose conjugate pairs. It's going to cancel out that middle stuff. So then all I have to do is the last times the last. I get negative 4, so I get negative 1. So this, if I multiply these together, I now have a rational number. I've rationalized that number. We're going to do the same process here to rationalize the numerator, so then maybe I can work with it and tease out that x minus 3. So watch what I mean here. This is our second of 3 methods. Okay. I am allowed to multiply the top by anything I want. I'm going to choose that because I know it's going to rationalize it. If I multiply the bottom by the same thing, then I won't change the value of the function. I'll just be changing the look of it. The goal here is to cancel out x minus 3. Remember, that's the goal, right? So on the bottom, I'm not going to do any multiplication. I have a binomial times a binomial, but I'm not going to multiply them out. I want to leave it factored because I want to cross off that x minus 3. You got to do that. That's a key step. Key step. Don't do anything on the bottom. Just write it. I want to cancel that x minus 3. That means an x minus 3 must appear up top. So now I have another binomial times a binomial up top. So I do first times first. Root x plus 1 times root x plus 1 is root x plus 1 squared, which is just x plus 1. The root and the square cancel. Or a root times itself is just the thing, right? Root 3 times root 3 is just 3. Now, the middles I'm not going to do. This root times that is a positive version of that, and then this times that root is the negative version of the same thing, so they're just going to cancel out. That's why I chose this. So notice I have no more square roots in the numerator. I've just rationalized it. I do have to do the last step where I do last times last, and I get negative 4. So look, this is now rationalized. No square root in it. And now I can mess with it and try to tease out that x minus 3. Well, now from here, it's pretty darn easy to see how it's x minus 3. I can just do the 1 minus the 4. I've done my fancy algebra footwork so that I can cancel those out. Remember, if there's nothing left on top, it's a 1 because you're doing division. I've just made my agreeable function. This function and this function are exactly the same everywhere, except they differ at the hole, at the target value 3. My iPad just froze. That's awesome. Hold on, let me try to fix that. Okay, I think I got it fixed. So I just filled the hole. So this is my original function. By canceling out that x minus 3, all I did was fill it in and make it continuous now. And those limits of those two functions are still the same. So now I'm just going to find the limit of my new function. And since it's continuous, I can cheat it by just doing direct substitution. I get 1 over 2 plus 2. I get 1/4. And that's the fancy footwork for that one. So there's going to be a couple types that you see. You'll see a polynomial divided by a polynomial. Typically what you do there is you factor. The other type you'll see is one with a square root in the numerator. And you have to rationalize the numerator and see if you can work with it then. And then now I'm going to look down here to show you some of the examples we were going to do. You can see these are like direct substitution. This one might be a factor one that we just talked about, so direct substitution is going to fail. Direct substitution is going to fail. This is a factor one. I don't know if it's going to fail in this one or not. We'd have to see. But this guy, it's going to fail. Maybe we have to factor it. This one, it's going to fail. We've got to rationalize the numerator. This one, it's going to fail because when I put in 1, I get 0 on the bottom. So I'm assuming I also get 0 on top. So I'm going to have to rationalize the numerator. So you can see those are the types. This is the third type that we did not talk about. We'll go through it when I do these examples. I'm going to do all these examples with you in our next video. I wanted to make a separate video that just works through these examples. The other type of function that we have to deal with that I haven't talked about yet is this piecewise function. So we're gonna do that in our next video. Some of our worked examples. Thank you.